Most people assume that the smallest objects in the universe are the ones with the least going on inside them. The bigger the object, the more there is to find in it. A galaxy contains more than a star. A star contains more than a planet. A planet contains more than a grain of sand. But here is what they left out. There is an object, roughly the size of London, weighing twice as much as our entire sun, made of the leftover core of a dead massive star, in which matter is layered into states physicists have had to invent new categories to describe. The same object spins 700 times a second. The same object has a magnetic field 100 billion times stronger than anything you have stood near. And the same object, at its center, contains a form of matter nobody has yet identified, possibly the densest material the universe is capable of producing before it gives up and becomes a black hole. The smallest thing in the catalogue may be the strangest. Get cozy. Subscribe if you haven't yet, because by the end of this, the word neutron will mean something you have never heard it mean before. Now, let's slowly slip into this. Part 1. The Sun is the easy case. It is Christmas Eve, 2024, and a small piece of metal is the closest thing humanity has ever placed near a star. The Parker Solar Probe, no larger than a small car, is hurtling through the outer atmosphere of our Sun at 200 kilometers per second. It is 6 million kilometers above the visible surface. That sounds far. It is not. It is closer than anything we have ever sent. It is inside the corona, the wispy outermost layer of the Sun, the place where the solar wind is born, the place where mountains of subatomic shrapnel are flung outward as coronal mass ejections, the place where a single one of those ejections, when it reaches Earth and tears at our magnetic field, can take down power grids on a continent. Below the corona, if the probe could descend, it would pass through a thin, warm layer called the chromosphere. The chromosphere is about 5,000 degrees Celsius. Below the chromosphere is the photosphere, which is the layer your eyes register when you look at the Sun without a filter. The photosphere is not solid. There is nothing solid anywhere in the Sun. The photosphere is plasma, churning, boiling, a cauldron of charged particles bubbling up from deeper layers and sinking again, all of it driven by heat coming from a furnace that lies far below. The probe will never go any deeper than the corona. It cannot. The heat would melt it long before it touched the photosphere, and even if it could survive the heat, the radiation pressure and the gas density would crush it. But you can ask, even if you cannot get there, what is going on below? And in fact you have to ask, because the question of what is going on at the center of the Sun turns out to be the same question, in a stretched and warped form, as the question this whole video is about. The question is, what holds a star up against itself? Every star you have ever seen is, in some sense, a tightrope walker. There is a force pulling its material inward, and there is a force pushing its material outward, and the star is the temporary, billion-year-long balance between the two. The inward force is always gravity. The outward force depends on what the star is made of and how it is arranged. In the Sun, the outward force is thermal pressure, generated by nuclear fusion in the core. In a white dwarf, the outward force will turn out to be something much stranger. In a neutron star, the outward force will turn out to be something stranger still. And at the very center of a neutron star, in the place this video is traveling toward, the outward force is something we do not yet have a name for. Possibly several somethings. We will get there. But for now, hold the image of the tightrope. It is the central image of this video. Everything we are about to discuss is a different kind of rope, holding up a different kind of weight. The Sun is the easy case. The Sun is the case where the rope is held by heat. Most of the universe is held up by ropes that are stranger than that. You can think of the inside of a star like a building. Each floor has a maximum capacity. The deeper you go, the heavier the floors above press down on the floor you are standing on. In an ordinary building, the floors are held up by columns and walls. In a star, the floors are held up by pressure, by the constant outward push of particles, bumping into other particles, exchanging energy, refusing to be squeezed any closer. As you descend through the layers of the sun, the pressure rises, and the density rises, and the temperature rises, and at every level the outward pressure is exactly enough to keep the inward pull of gravity from advancing any further. The technical name for that balance is hydrostatic equilibrium. Physicists also call it the equation of state. The equation of state describes the relationship between pressure, density, and temperature in any given layer of a star. Different materials have different equations of state. A loose gas has a soft equation of state, meaning it compresses easily. A solid has a harder one. A degenerate gas, which we will meet shortly, has an even harder one. And at the center of a neutron star, the equation of state is the central mystery of this whole video. It is the unknown number in the balance. We will learn by the end of tonight that we have very precise observations of neutron stars and very imprecise ideas about what is inside them, and the gap between the two is exactly the gap that the equation of state is hiding in. But the sun is the easy case. The sun has been measured and remeasured, and its interior is one of the best understood places in the universe. Astronomers know its core temperature to 3 significant figures. They know its density profile from surface to center with extraordinary precision. They know what is in it, layer by layer, and they cannot see any of it. The sun is opaque. Light produced in the core takes, on average, 170,000 years to claw its way out to the surface. The photon that left the center of the sun the year you were born will not reach the photosphere for the rest of your life, and your children's lives, and theirs, and so on for thousands of generations. Whatever happens deep inside the sun, we do not see it directly. We see it second-hand, much later. So how do we know the core temperature to 3 significant figures if we cannot see the core? That is the part of the story we are about to come to, and it involves a man born to a poor family in a place that is now Bangladesh, in 1905, expelled from school for political reasons, who would eventually write down an equation that lets you read the contents of a star from 1,000 light years away. It also involves a particle so antisocial, so ghostly, that 1 trillion of them just passed through your body in the time it took you to read this sentence, and another 1 trillion just after that, and you noticed none of them. And it eventually involves a kind of stellar death that produces an object so dense that what we are about to describe will sound made up. The sun, again, is the easy case. The sun's tightrope is held by heat. By the end of this video, you will have walked all the way down to a place where the tightrope is held by something nobody has ever seen, and nobody can replicate in any laboratory, and the universe has only allowed us to observe by listening to it ring through the fabric of space-time itself. The walk will be long. The walk will be slow. You do not need to keep track of every number. You only need to keep the image of the tightrope in mind. We start with one of the people who first taught us how to read a star. Part 2. The Indian schoolboy who read the stars. It is 1905, and Lord Curzon is sitting hunched over a map of southern Asia in Calcutta. He is the Viceroy of India, the direct representative of the British Crown in this part of the empire, and he has a problem. The Bengali population is becoming increasingly vocal in its resistance to British rule. His eventual answer to that problem is to draw a line through Bengal, dividing it into a Hindu West and a Muslim East. The plan does not solve the problem. The plan makes the problem much worse. It also helps shape, in a way Curzon will never know, the future of stellar physics. Among the many people whose lives are disrupted by the partition is a teenager named Meghnad Saha. Born to a poor family in Dhaka, which is now the capital of Bangladesh, Saha has earned a scholarship to the Dhaka Collegiate School, which is run by the British. He is brilliant. He is also, at 15 years old, politically active. When the partition triggers boycotts of British goods and demonstrations against British rule, Saha takes part in them, and the British school promptly expels him for doing so. It is a setback. It will not be the only one in his life, but it is, by his later admission, the moment that shapes his entire political identity. He will remain an active campaigner for Indian independence for the rest of his life, even as he becomes one of the most important astrophysicists of the 20th century. By 1923, Saha is a professor at the University of Allahabad, and he has done the work that today bears his name. The Saha ionization equation tells you, for any given temperature and pressure, how many of the atoms in a sample of gas are going to be torn apart. To understand why that matters, you need a small detour into what an atom actually is, because the same picture is going to come back to us in stranger and stranger forms all the way down to the center of a neutron star. The simplest picture of an atom, and let us be honest, it is too simple, but it will get us where we need to go, is a small, heavy nucleus in the middle, made of positively charged particles called protons and neutrally charged particles called neutrons, with a cloud of negatively charged electrons orbiting around it. The negative charges of the electrons exactly cancel the positive charges of the protons, so the whole atom is electrically neutral. The opposite charges also attract each other, which is what keeps the electrons bound to the nucleus rather than flying off into space. Now give the electrons an energy boost. Heat them up, for example, by raising the temperature of the gas they are part of. At some point, the electrons gain enough energy to break free of the attraction holding them in orbit. Like a country breaking free of colonial rule, they declare their independence. They drift away from their nuclei, and what is left behind is a soup of bare nuclei and free electrons, all of them charged, all of them moving fast. Physicists call this soup a plasma. Saha's equation tells you, for a given temperature and pressure, exactly how much of the gas has gone plasma and how much is still ordinary atomic gas. At school, you may have learned that there are 3 states of matter: solid, liquid, gas. That is not wrong, but it is incomplete. Plasma is a 4th state, and depending on how you count, there are several more. We will meet some of the others further down. The first one Saha's equation tells us about is the one most of the visible universe is actually made of. By mass, somewhere between 99.9 and 99.99% of the visible universe is plasma. The visible universe is made of stars, and stars are mostly plasma. The Earth and the planets are an exception, not the rule. You live on a small clump of solid material, orbiting through a universe that is overwhelmingly a sea of stripped atoms. Saha's equation lets you take any layer of any star, plug in the temperature and the pressure, and calculate exactly which elements are ionized and to what degree. That is enormously powerful. Combined with the spectra of stars, the patterns of light absorbed and emitted at characteristic wavelengths by different elements, Saha's equation lets you read the composition of a star without ever going near it. You take a slice of starlight, you spread it out into its colors, you read the dark lines and the bright lines where atoms are absorbing or emitting at particular wavelengths, and Saha's equation tells you what those lines mean. You can do this for stars thousands of light years away. You can do it for stars that died before humans existed. Saha's equation, in a real sense, made stellar interiors knowable from the outside. For the Sun, Saha's equation tells us something specific about the photosphere, that bubbling visible surface at 5,500 degrees Celsius. At that temperature, the photosphere is only partially ionized. Most atoms still have most of their electrons. Some atoms have lost some of their electrons. There is plasma here, but it is mixed with ordinary hot atomic gas. To find a region of the Sun that is fully a plasma, we have to drop deeper, where the temperature climbs above about 10,000 degrees Celsius. And to find a region where the plasma is so dense it starts behaving in strange new ways, we have to drop deeper still. To do that, we descend into the core. The Sun's core occupies the inner quarter of its radius. It is hard to overstate just how extreme the environment inside that core actually is. The pressure is 250 billion times Earth's atmospheric pressure. The plasma there is squeezed to a density of 150 grams per cubic centimeter. Gold, the densest of the common metals you might encounter in daily life, comes in at 19.3 grams per cubic centimeter. The Sun's core is almost 8 times denser than gold, and it is made mostly of ionized hydrogen, which is the lightest element in the universe. A single tablespoon of solar core material would weigh as much as a newborn human baby. If you could fill an Olympic-sized swimming pool with the stuff, it would weigh more than the Titanic, with all of its passengers and cargo included. By every intuition you have ever had about the behavior of matter, this should not be stable. Gravity, given the chance, would crush the core down further. The reason it does not is the same reason the whole star does not collapse. The outward pressure from the heat and the radiation in the core is exactly enough to balance the inward pull. The Sun is in hydrostatic equilibrium. The tightrope is taut and steady. It will remain steady for billions of years. But where does the heat come from? Why is the core hot enough to generate that outward pressure in the first place? The answer is the second great discovery in the long story of stellar interiors, and it brings us into the era of nuclear physics. Every second, in the core of the Sun, 620 million tons of hydrogen are squeezed together by the pressure of the overlying layers until 4 protons fuse, in a multi-step process, into a single helium nucleus. The output of that fusion is 616 million tons of helium and a small amount of leftover mass that has been converted by Einstein's famous equation into energy. 4 million tons of matter become pure energy every second. That is a colossal amount of energy. It is the source of all the heat and all the light that the Sun produces. It is also, in the form of outward pressure, the only reason the Sun has not already collapsed under its own gravity. The fusion is the engine of the star, and it is also the star's tightrope walker. Without the fusion, gravity would win and the tightrope would snap. Now, the energy produced in the core does not leave the Sun easily. Light in the core has to fight its way outward through one of the most opaque environments in the universe. The plasma is so dense, and the photons are absorbed and re-emitted so many times along the way, that the light from a single fusion event takes, on average, 170,000 years to reach the surface. The sunlight on your skin tonight was generated in the core when humans were not yet anatomically modern. The Sun is a fossilized radiator. There is, however, one kind of particle that does not get held up by the plasma. Almost nothing held it up. It travels through the entire Sun, from the core to the surface to space and beyond, almost without interacting with anything along the way. It is so antisocial that it can pass through a light year of solid lead with only a 50% chance of being stopped. It is called the neutrino, and it is the only direct messenger we have from the deepest interior of any star. It is the next part of the story. Part 3. The ghost particles that read the furnace. The Sun's core produces neutrinos in obscene quantities. Every second, the fusion reactions that fuse hydrogen into helium release 179 trillion of them. That number, written out, has 38 zeros. They pour out of the Sun in every direction, and because they almost never interact with ordinary matter, they pass through the rest of the star as if it were not there. From the moment a neutrino is born in the core to the moment it leaves the surface of the Sun is a journey of about 3 seconds. Compare that to a photon, which takes 170,000 years. Compare that to the neutrino's leisurely outward speed of approximately the speed of light. The neutrino's path is not impeded. It does not bounce. It barely notices the sun exists. After it leaves the sun, it travels in a straight line at the speed of light until it reaches something. If that something is the Earth, the neutrino almost certainly passes through it without interacting. Hold your hand up toward the sun, and the number of solar neutrinos that pass through your thumbnail in a single second is greater than the number of human beings on the planet. The total number of neutrinos that will pass through your body over the course of your entire life is roughly equal to the number of stars in the observable universe. You are being continuously washed in a flux of ghost particles from the heart of the sun, and you do not notice any of it. Until the 1960s, neutrinos were considered theoretical. Wolfgang Pauli had proposed the existence of a particle like this in 1930 as a desperate fix for a problem in nuclear physics, and had famously written to a colleague apologizing for inventing something he believed could never be detected. By the 1950s, however, the particle had been confirmed in laboratory experiments, and by the 1960s, a physicist named Raymond Davis built a tank of cleaning fluid deep underground in the Homestake gold mine in South Dakota and started counting the trickle of solar neutrinos that interacted with chlorine atoms in the tank. He counted about 1/3 of the number that the standard model of the sun predicted. For 30 years, this was called the solar neutrino problem. The eventual resolution, in 1998, at the Super Kamiokande detector in Japan, and then conclusively, in 2001, at the Sudbury Neutrino Observatory in Canada, is one of the most beautiful results in modern physics. The sun was producing the right number of neutrinos. The neutrinos were changing flavor. On their way out, there are 3 kinds, called electron, muon, and tau, and the sun produces only electron neutrinos, but by the time they reach Earth, they have oscillated into a mix of all 3. Davis's detector could only see electron neutrinos. He was missing 2/3 because 2/3 had become something else. This required neutrinos to have mass, which the original theory had said they did not. The standard model of particle physics had to be modified to accommodate it. 2 Nobel Prizes were awarded for the work. For us tonight, what matters is not the oscillation story, but what it implies. We can detect solar neutrinos. We can count them. The number that arrive at Earth is exquisitely sensitive to the temperature in the sun's core. If you tweak the core temperature, even slightly in the model, the number of neutrinos produced changes dramatically, because the rate of nuclear fusion depends very strongly on temperature. So the neutrino count is a thermometer for the center of the sun. By measuring how many solar neutrinos hit a detector on Earth, you can read the core temperature to high precision. The current value is 15.7 million degrees Celsius. That is the temperature in the deepest part of the easiest case. That is the easy number we will be carrying with us as we descend into stranger and stranger stars. The neutrino is also, more generally, the messenger physicists trust for the inside of stars. It is the only particle that gets out of dense stellar interiors quickly enough to carry current information. Photons get scattered for tens of thousands of years before escaping. Neutrons and protons cannot leave at all. Everything inside a star is locked in, except the neutrinos. The sun's interior is the closest place in the universe where this kind of measurement has been routinely done, and the sun is now the calibration point for every other stellar interior we try to understand. When astronomers want to model a star they have never seen up close, and they have never seen any other star up close, they tune their models against the sun and then extrapolate. The sun is the benchmark. It is the easy case. And there is one more thing the neutrinos teach us, which we will need for later parts of this video. They teach us that even the deepest part of a star can be read from outside, if you have the right tool. Photons are not the only kind of light. Gravitational waves are not the only kind of ripple. The universe sends out information about its hidden interiors in many forms, and our job, as a species that wants to understand it, is to invent the instruments to listen. Neutrinos are one of those instruments for the Sun. Gravitational waves are another instrument for neutron stars. We will get to gravitational waves much later. For now, hold the principle. The inside of a star is not entirely hidden. It only seems hidden until you find the right kind of signal. So what does the easy case actually look like, summarized in one image? Picture a sphere of ionized hydrogen, 400,000 kilometers in radius, churning under its own weight. In the outermost layers, the plasma is wispy and hot. As you descend, the density rises and the temperature rises, slowly at first and then much faster. At the boundary of the convection zone, about a third of the way in, the plasma stops bubbling and starts radiating instead. By the time you reach the core, which occupies the inner quarter of the radius, the pressure is 250 billion atmospheres, and the density is 150 grams per cubic centimeter, and the temperature is 15.7 million degrees. Hydrogen is fusing into helium at 620 million tons per second. 4 million tons per second are converted into pure energy. The energy generates the outward pressure that holds up the entire weight of the star above. The neutrinos pour out at 179 trillion per second, carrying the temperature of the core out into the universe at the speed of light. This will go on for about another 5 billion years. The Sun has been doing this for 4.6 billion years already, and it has roughly that much fuel left in the core. After that, the easy case stops being easy. What happens next is a slow, ugly, beautiful, drawn-out death. The hydrogen in the core runs out. Fusion temporarily ceases. The outward pressure that was holding the Sun up disappears. Gravity, which has been politely waiting for billions of years, takes another step inward. The core contracts. The contraction heats the surrounding hydrogen shell, which lights up and starts fusing on its own, and the outer layers of the Sun puff up enormously into a red giant phase that will swallow Mercury and Venus and probably scorch Earth. Eventually, when even the helium in the core runs out, the outer layers will detach completely and drift away into a beautiful, intricate cloud called a planetary nebula. What is left behind is the core, not the original core, the contracted, compressed, much denser core that remains after the outer layers have departed. That leftover core is no longer a place where fusion happens. There is no fuel left. There is no engine. There is nothing producing outward thermal pressure. By all the rules of hydrostatic equilibrium we have been using so far, the leftover core should collapse the rest of the way under its own gravity. It does not collapse. It stops at roughly the size of the Earth, holding about half the mass of the original Sun in a sphere the size of a small planet. The density is about 1 billion kilograms per cubic meter. A sugar cube-sized chunk of it weighs as much as an elephant. A shipping container's worth weighs as much as the Great Pyramid of Giza. What is holding it up? Gravity should win here. Heat is not doing the work. There is no fusion, no engine. The outward thermal pressure that supported the Sun for 10 billion years is gone, and yet the dead core does not collapse. It sits there, white hot, slowly radiating away its leftover heat for tens of billions of years. Something is holding it up. Something that is not heat. Something nobody had ever needed to talk about before. We call those objects white dwarfs. And to understand what holds them up, we have to follow a young British physicist who was wounded at Gallipoli into a hospital, then into a lab, then into one of the strangest insights in early 20th century physics. Part 4. Sirius and its pup. If you live in the Northern Hemisphere and you step outside on a clear winter night, the brightest star in your sky is Sirius. It is also one of the most theatrical. It twinkles violently. It flickers through reds and greens and blues that no other star in the sky reaches. Some of that is because Sirius is bright enough that its color shifts are visible to the unaided eye where dimmer stars wash out. Some of that is because Sirius is fairly low in northern winter skies, so its light travels through a longer column of turbulent atmosphere on its way to your eyes, and the atmosphere acts as a prism. Either way, Sirius is impossible to miss. Sirius has been important to almost every culture that has had a night sky. The ancient Egyptians timed the flooding of the Nile to the heliacal rising of Sirius, which is the morning it first becomes visible again after a long absence behind the sun. The Romans called the late summer the dog days because Sirius, the dog star, the brightest star in the constellation Canis Major, was rising with the sun in those months. The phrase "the dog days are over" comes from the moment in late July when Sirius and the sun stop sharing the sky and Sirius disappears for a while. None of this concerns us tonight, except as a reminder of how long humans have been paying attention to this particular star and how recent is our understanding of what is actually going on out there. Because Sirius, it turns out, is not alone. It has a companion. The companion is much fainter, and you cannot see it without a telescope, and the two stars orbit each other every 50 years. The companion is called Sirius B, but its informal name in the years after its discovery was simply the Pup, because Sirius itself is the dog star. The Pup was first detected by Friedrich Bessel in 1844, when he noticed Sirius wobbling as it travelled across the sky. Something invisible was tugging on it. 18 years later, the Pup was directly seen for the first time through a telescope at the Dearborn Observatory in Chicago. It was very faint. It was clearly there. By the early 20th century, the Pup had become a puzzle. Spectroscopic measurements showed that it was hotter than the sun. Brightness measurements showed that it was much smaller than the sun. The combination did not make sense. A hot, small object that is faint compared to a cooler, larger object suggests that the hot one is much, much smaller. By 1922, when the Dutch astronomer Willem Jacob Luyten coined the term white dwarf to describe these objects, the size estimates had become alarming. The Pup is about the size of the Earth. It has the mass of the Sun, and it is so dense that 1 cubic centimetre of it weighs about a ton. A sugar cube of the Pup weighs as much as an elephant. A small shipping container's worth weighs as much as the Great Pyramid at Giza. Sit with that for a second. The Pup is a star. It is not a planet. It is shining, white hot with its own light. But it is the size of a planet. It is denser than anything on Earth by many orders of magnitude. And it is, by any honest reckoning of physics in the early 1920s, an object that should not be stable. In the Sun, as we have discussed, the outward push that holds the star up against gravity comes from heat. The plasma in the core is at 15.7 million degrees, and nuclear fusion is generating fresh heat every second. Take away the fusion, and the heat eventually drains out, and gravity wins. The Pup is not fusing anything. There is no nuclear engine in there. The Pup is simply the leftover core of a dead sun, cooling slowly over tens of billions of years. By the time we got to looking at it in the 1920s, the leftover heat in the Pup was nowhere near enough to generate the kind of outward pressure that would be needed to support its own weight. If hot thermal pressure were the only thing holding stars up, the Pup should already have collapsed. But the Pup had not collapsed. It was sitting there, in the sky, the same size as the Earth, perfectly stable, glowing white hot. Something else was holding it up. Something other than heat. Nobody had any idea what. This is the moment where stellar physics ran into a brand new branch of physics that was being invented at almost exactly the same time. The early 1920s were an extraordinary period for what we now call quantum mechanics. It is a decade most people remember for jazz and flappers and prohibition and speakeasies. It was also the decade in which Werner Heisenberg and Erwin Schrödinger were writing down the wave equations of quantum mechanics. The decade in which Niels Bohr was running his institute in Copenhagen as the world center of the new physics. The decade in which Wolfgang Pauli was working out one of the strangest and most consequential principles in all of science, the principle that would eventually explain not just the white dwarf, but every layer of every neutron star you are about to descend into. Pauli's principle is called the exclusion principle, and the rough idea is this. In the quantum world, particles do not behave like the small, hard balls of classical physics. They behave like something stranger. Each particle has a set of quantum numbers that describe its state, its energy, its angular momentum, its spin direction. Pauli noticed that certain particles, including electrons, follow a strict rule. No two of them can ever share the exact same set of quantum numbers at the same time in the same system. Each particle has to occupy a unique state. You can have as many electrons as you like in an atom, but each one has to be in a slightly different configuration. The easiest way to picture this is by imagining a tall building. The Chrysler Building in New York is a useful image. Each floor of the building represents one of the possible energy levels an electron is allowed to have, and each floor has a maximum capacity. If everybody in the city wants to spend the night in the building, the lower floors fill up first. Once the ground floor is full, the next people who arrive have to take the first floor. Once the first floor is full, the next group has to climb to the second, and so on. There is no way to squeeze 100 people into the lobby, no matter how hard you push. The fire code does not allow it. The laws of quantum mechanics, similarly, do not allow two electrons to share a single state. In an ordinary gas, this rule almost never matters. The particles are spread out enough that they have plenty of room, and the available quantum states vastly outnumber the particles trying to occupy them. The exclusion principle is in effect, but it never gets triggered. In a much denser environment, however, like the leftover core of a dead star, the situation changes. The available quantum states fill up. The lower floors of the building are completely occupied, and gravity, trying to compress the gas further, runs into a wall. The wall is not made of heat. It is not made of any classical force. It is made of the simple geometrical fact that there are no more low-energy states for the electrons to be squeezed into. They cannot get any closer together. The exclusion principle is in effect, and now it is bearing weight. The physicist who first applied this principle to white dwarfs and saw what it meant was a young Englishman who almost did not survive the First World War. He took a bullet to the shoulder in the trenches of Gallipoli in 1915. He was 26 years old. He had been a mathematician at Cambridge before the war. He came home, recovered, and worked for the British military on anti-aircraft ballistics until the war was over. He turned out to be the man who held the pup up. His name was Ralph Fowler. He never received the Nobel Prize. He died too young, at 55, before the importance of his insight had quite settled into the consensus of the field. But Subramanian Chandrasekhar, who built directly on Fowler's work and did receive the Nobel, wrote about Fowler at his death that his work showed what theoretical astrophysics at its best could be. A combination, Chandrasekhar said, of rare physical insight and mathematical precision. Fowler is the reason we know what is inside the pup. He is also, eventually, the reason we know what is at every layer above the very core of a neutron star. We owe most of this video to him. He arrived at the answer through the slowest possible route. He was wounded in Turkey by a bullet from a German rifle in a war fought over the partition of an empire. The wound put him in a hospital. The hospital put him in the path of a biophysicist named Archibald Hill. Hill recruited him into a team of scientists working on artillery, the so-called Hill's Brigands, which also included a son of Charles Darwin. After the war, when Fowler returned to academia, his interest had shifted from pure mathematics to physics, and his physics interest, fed by Hill, drew him into the new quantum mechanics being developed in the 1920s. Fowler took the exclusion principle, which had been formulated to explain why electrons in atoms occupy specific shells, and applied it to a much larger system. He asked what happens when you have not a single atom, but a star's worth of electrons all crushed together at extraordinary density. The answer, which he published in a paper in 1926, is that the electrons resist further compression with a force that is much stronger than ordinary thermal pressure. The force does not depend on temperature. You could chill the gas to absolute zero and it would still push back. The force depends only on density. The denser the gas, the harder it pushes. We call it degeneracy pressure. The matter is called degenerate matter, and it is the only reason the pup is still up there in the sky. Part 5. Standing on a white dwarf in the dark. Let us walk this slowly, because the idea is strange enough that walking quickly past it would do it a disservice. Imagine you are standing on the surface of a white dwarf Sirius B, the pup, the size of Earth and the mass of the Sun. The horizon, if you could see it, is hot twice the temperature of the surface of our own Sun, glowing white with the leftover heat of a dead stellar core. There is no nuclear fire below your feet. There is no engine churning away beneath the crust. The star is the size of a planet, and it is glowing only because it is cooling slowly from the leftover heat of its own death, and it will continue cooling for tens of billions of years before it finally goes dark. The crust beneath you, if you could imagine standing on it without being instantly atomized, is crystalline carbon and oxygen, a planet-sized diamond, still warm. The pup is, in a literal sense, the world's largest unfaceted gemstone. The light reflecting from its surface is the light of its own leftover heat, re-emitted from a carbon crystal lattice that has been compressed by stellar gravity into a single rigid block. You bend down to pick up a sample. The chunk in your hand weighs as much as a small skyscraper. You let it drop. It does not fall the way you expect. Gravity here is 100,000 times Earth's, and the sample slams into the crust with a sound you cannot hear because the atmosphere is too thin to carry it. The thing that keeps this entire structure from collapsing further is not heat. There is no heat doing any work here. What holds the pup up is the simple, geometrical refusal of the electrons packed cheek by jowl into every quantum slot. The laws of physics will allow to share a single state with each other. It is a quiet refusal. It is also holding up a star. Hold that image for a moment. The pup is, for our purposes tonight, the first encounter with a tightrope that is not held up by heat. Every other star we have discussed so far has been balanced by thermal pressure. The pup is balanced by something quantum. It is the first hint that the universe has other tools for keeping matter intact, and that those tools become important precisely when the more familiar ones run out. We will see this pattern again in neutron stars. The pattern is when one form of resistance fails, another, stranger form, takes over. Each safety net is more exotic than the last. Each one operates at a smaller scale of particle, and each one has a breaking point of its own. For the pup, the safety net is electron degeneracy. Electrons cannot share quantum states, so once you have packed them as tightly as the exclusion principle allows, they push back against any further compression with a pressure that does not depend on temperature. You could cool a white dwarf to absolute zero and it would still be the same size, because the support is not coming from heat. The pup will radiate away its leftover heat for tens of billions of years, slowly fading to black, but its size will not change. By the time it has cooled to the temperature of the surrounding interstellar medium, it will have become what physicists call a black dwarf, a planet-sized chunk of crystalline carbon held up by quantum refusal alone. The universe is not yet old enough for any white dwarf to have cooled that far. Every white dwarf that exists today is still actively radiating. But Fowler's discovery, beautiful as it was, had a hidden caveat that he himself did not fully explore. The pup is held up by electron degeneracy pressure. But electron degeneracy pressure has a limit. It can only support so much weight. If you pile too much mass onto a degenerate electron gas, the resistance eventually fails, not in the sense that the gas runs out of states, but in the sense that the resistance is overcome by the gravitational pressure. The calculation of exactly where that limit lies was done by a young Indian physicist named Subrahmanyan Chandrasekhar on a long boat journey from Madras to England in 1930. He was 19 years old. He was on his way to begin his graduate work at Cambridge. He had several weeks of nothing to do, and he spent them working through the equations of degenerate matter, asking how heavy a white dwarf could possibly be before electron degeneracy pressure broke down. The answer he calculated was 1.4 solar masses. Above that limit, no white dwarf can exist. Above that limit, the electrons cannot hold the star up, no matter how tightly they are packed. It is hard to convey just how unwelcome this result was. Eddington, who was the Dean of British Astrophysics at the time, refused for years to accept it. He attacked Chandrasekhar publicly. He found the implication so strange that he assumed there had to be an error in the relativistic correction Chandrasekhar had used. There was no error. The Chandrasekhar limit was correct, and it is now one of the foundational numbers in stellar evolution. Above 1.4 solar masses of degenerate matter, electron degeneracy pressure fails, and the leftover core of a sufficiently heavy star cannot stop at the white dwarf stage. It continues to collapse. What happens next is the next layer of our descent. When the gravity wins over electron degeneracy pressure, the collapse does not stop. The electrons get crushed harder and harder against the protons. At a certain density, an extraordinary thing happens. The electrons and the protons combine. Each electron is forced into a proton, and the two together become a neutron. This process, called electron capture or inverse beta decay, releases a neutrino, another contribution to the universe's vast traffic in ghost particles, and it converts the entire core of the dying star into a single mass of pure neutrons. But neutrons, like electrons, are fermions. They also obey the Pauli exclusion principle. They also refuse to share quantum states. So once the core has been converted entirely into neutrons, the same quantum refusal that held up electrons in a white dwarf now takes over at a much smaller scale. The neutrons resist further compression. The collapse stops again. The leftover core stops at a radius of perhaps 10 or 12 kilometers, holding between 1 and 2 solar masses of pure neutron matter. We have reached the next safety net. We have reached the neutron star. We are not yet inside it. We are only looking at it from the outside. But before we descend, we should pause to acknowledge who first predicted these objects, because the prediction came years before any of them were observed. The names are Walter Baade and Fritz Zwicky. The year is 1934. The paper appears in the Proceedings of the National Academy of Sciences, and it makes two claims. The first is that supernovae, the violent explosions in which massive stars die, release energies far beyond ordinary novae and represent a distinct class of cosmic event. The second is that the remnants of those explosions are extremely compact objects, made entirely of neutrons, the existence of which is required by the energy budgets they are calculating. They name them neutron stars. Zwicky, the same year and the year before, depending on which paper you cite, coins the term dark matter for the unexplained extra gravity he was observing in the Coma Galaxy cluster. He is having a busy decade. His two big ideas, dark matter and neutron stars, will both turn out to be central to our story tonight, although nobody in 1934 would have predicted that they would intersect at the center of a dead star, inside the very objects he was proposing. For most of the next 30 years, neutron stars remained a theoretical curiosity. The objects were too small, too cold, and too faint to detect with the telescopes of the time. There were occasional speculations about them in the literature. There were a few calculations of their expected properties, but there was no observation, there was no direct evidence that any of them actually existed. The idea was beautiful, the calculations were consistent, and the universe had so far declined to confirm it. That changed in 1967 in Cambridge, when a graduate student named Jocelyn Bell Burnell, scanning data from a radio telescope she had helped to build, noticed a strange repeating signal coming from a particular direction in the sky. The signal pulsed every 1.33 seconds with astonishing precision. It was so regular that her first hypothesis, which she labelled in her notebook only half-jokingly, was that the signal might be artificial. The provisional designation in the lab was LGM-1, which stood for Little Green Men No. 1. The seriousness of the joke wore off quickly. Within months, she had found additional sources in other parts of the sky, all with similarly precise pulses, but at different periods. It was clear that there was a class of natural objects out there that was sending out very regular radio pulses. The question was, what could be regular enough to do that? The answer, which emerged within a year, was that these were neutron stars. Specifically, they were rotating neutron stars whose magnetic fields were channeling beams of radiation out from their poles. As the stars rotated, the beams swept across the sky like the beam of a lighthouse. When the beam happened to point at Earth, we detected a pulse. The faster the star rotated, the more frequent the pulses. The objects were named pulsars, which is a contraction of pulsating stars, and they were the first observational confirmation that Bardet and Zwicky's neutron stars actually existed. That was the gateway. The neutron star, which had been a theoretical curiosity for 3 decades, suddenly had a name, a sound, an observational signature, and a place in the sky you could point to. We are about to walk into one of them. Part 6. The City in the Sky. The Crab Nebula is one of the most photographed objects in the northern sky. If you start at Sirius, the brightest star, and look up and to the right, you will hit Orion's belt, those 3 bright stars in a near-perfect line that have anchored constellations in human culture for as long as humans have looked at the sky. Continue on the same line beyond Orion's belt, and you reach a V-shaped cluster of stars called the Hyades. The V is the head of the constellation Taurus, the bull. From the tip of the bull's left horn, very close to a star called Zeta Tauri, you will find the Crab Nebula. With a small telescope, it appears as a faint, irregular smudge. With a long exposure photograph, it becomes one of the most photogenic objects in the cosmos, a sprawling, filamentary cloud of glowing gas in shades of red and green and blue, expanding outward from a small, bright point at its center. The crab is a supernova remnant. Almost 1,000 years ago, in the year 1054 of the Common Era, Chinese astronomers recorded the appearance of a brand new bright star in this exact patch of sky. They called it a guest star. It was visible during the day for nearly a month. It took 2 long years to fade from the night sky entirely. We now know that what they witnessed was the death of a massive star. The outer layers blew outward at speeds of thousands of kilometers per second, lighting up the surrounding interstellar medium and creating the cloud we see today. The bright point at the center of the cloud is what was left behind. It is a neutron star. To call a supernova merely super is to do it an injustice. In a few seconds, a supernova releases more energy than the sun will produce over its entire 10 billion year lifetime. The light from a single supernova can briefly outshine the entire galaxy that contains it. And these events are not rare. A supernova detonates somewhere in the observable universe roughly every 10 seconds. By the time this video ends, hundreds of them will have exploded. In our own galaxy, supernovae are much rarer. The Milky Way produces perhaps 1 or 2 per century, and many of them are obscured by intervening dust clouds and never become visible from Earth. The most recent confirmed galactic supernova that anyone witnessed directly was SN 1604, observed by Johannes Kepler. There has not been a naked-eye galactic supernova since. We are overdue. Somewhere in our own galaxy, statistically, a massive star is collapsing into a neutron star or a black hole at this exact moment, and the light from the explosion is on its way to us. We do not yet know when it will arrive. But the Crab pulsar is here, in our sky, observable tonight. It is the neutron star at the heart of that 1054 supernova remnant. It is 21 kilometers across, which is roughly the same size as London and somewhat narrower than Tokyo. It is rotating 30 times per second. Its rotation is so precise that, when its pulses are recorded and sped up into the audible range, the sound is a steady drone. 30 Hz is in the lowest range of human hearing. The Crab pulsar is, in a real sense, audible, a single low note sung by a dead star for centuries. A neutron star is not a star in any usual sense. It is what is left after a star has died. It is the compressed, degenerate core of a massive star whose outer layers have blown away in a supernova. The mass of a typical neutron star is between about 1.3 and 2.3 solar masses. The radius is between about 10 and 13 kilometers. The density inside is around 400 million tons per cubic centimeter. A teaspoon of neutron star material weighs more than the combined mass of every human being who has ever lived. The numbers do not stop there. The gravitational field at the surface is roughly 2 trillion times Earth's. The escape velocity is around half the speed of light, 150,000 kilometers per second. On Earth, you need to be moving at 11 kilometers per second to escape the gravitational pull and reach space. On the surface of a neutron star, you would need to be moving 13,000 times faster than that. The gravity is so strong that any structure rising above the surface is immediately crushed back down. Mountains on a neutron star are, at the absolute maximum, a fraction of a millimeter high. The surface is one of the smoothest in the universe. Now imagine the planet under you shrinks. The Earth's diameter goes from 12,500 kilometers to 20. The mass stays roughly the same, then doubles. The horizon vanishes. The horizon is now perhaps 3 meters away, because the curvature of the gravity well bends the path of light into a tight circle around your head. If you look at your own feet, you see the back of your skull. The ground beneath your soles is smoother than glass, because the gravity is so strong that no mountain can rise more than a fraction of a millimeter above the surface. You are not standing on the surface, of course. If you were, your body would be flattened into a film about an atom thick. But imagine for a moment that you could. You hold out your hand and let go of a pebble from 1 centimeter above. It moves so quickly you cannot follow it. By the time it covers that 1 centimeter, it is moving at half the speed of light. It hits the ground in a flash of gamma rays, a small piece of energy returned to the star. The magnetic field around you is 100 billion times stronger than the strongest one you have ever stood inside. Above you, the sky is shifted. Light from distant stars is bent into a halo. You are not under the night sky anymore. You are inside the gravity well that is rewriting the night sky. Most neutron stars rotate. Some of them rotate slowly, with periods of seconds. Others rotate impossibly fast. The Crab pulsar, as mentioned, spins 30 times per second. The fastest known pulsar, PSR-J, 1748-2446 AD, spins 716 times per second. That is faster than the rotor of a household blender. A point on its equator is moving at a quarter of the speed of light. The theoretical breakup speed for a neutron star, the rotation rate at which centrifugal force at the equator would overcome gravity and rip the star apart, is around 1500 Hz. The fastest neutron stars we have observed are pushing about halfway to that limit. The rotation, combined with the absurd magnetic field, is what generates the radio pulses Bell Burnell first observed. The magnetic field channels beams of radiation out from the magnetic poles. As the star rotates, the beams sweep across the sky. If a beam happens to cross the line of sight to Earth, we see a pulse. If it never crosses our line of sight, we never see the star at all. There are vast numbers of neutron stars in the Milky Way that we have never detected, simply because their beams do not happen to point our way. The magnetic fields are themselves extraordinary. A typical neutron star has a surface magnetic field of around 10 to the 12 Gauss, which is 100 billion times the strength of a refrigerator magnet. A subclass of neutron stars, called magnetars, have fields 10,000 times stronger still, up to 10 to the 15 Gauss. The strongest magnetic field humans have ever produced in a laboratory is about 1 million Gauss, briefly, in pulsed experiments. The weakest neutron star is 1 billion times more magnetic than that. The strongest is 10 trillion times more magnetic. If a magnetar passed within a few hundred kilometers of the Earth, its magnetic field alone would distort the atoms in your body. Atomic electron orbits would deform. The chemistry of life would stop working. We are not in any danger of a magnetar coming near us. The nearest known one is several thousand light-years away. But the existence of these objects, and the routine observation of their flares, which can be powerful enough to disturb the Earth's ionosphere from across the galaxy, is a reminder that the universe builds objects whose properties are simply not comparable to anything we encounter in daily life. And all of this is just the surface. The 2 trillion G gravity, the half-light speed surface impact, the 30 Hz drumbeat in the audible range, the 100 billion-fold magnetism. These are the things you would notice from the outside, or while standing counterfactually on the crust. We have not yet gone inside. We have not yet asked what holds this whole structure together, or what is layered between the crust and the center. The descent into a neutron star is about to begin, and the layers we are about to encounter make everything we have discussed so far look almost familiar. Part 7. The atmosphere of diamond and the crust that burns. A small repair kit floats in the airlock of the International Space Station, waiting. It is January 2025. An astronaut, fully suited, helmet clipped firmly into place, gloves on, life support running, glides out into the void. The Earth fills half of their visual field, a marble of blue veined with white. They have 6 hours of consumables on their back. They have a job to do. Bolted to the exterior of the station is a washing machine-sized X-ray telescope called NISA, which stands for Neutron Star Interior Composition Explorer. It has been there since 2017, mapping the surfaces of distant neutron stars by detecting the X-rays they emit. Its thermal shields are 500 times thinner than a human hair. In May of 2023, something probably micrometeoroid impacts, possibly contamination from a thruster firing, possibly both punched a series of holes in those shields. The largest was the size of a postage stamp. Sunlight had been leaking into the telescope ever since, washing out its measurements and making it useless for the precision work it had been built to do. NISA was never designed to be repaired in orbit. There were no service handles. The shields had not been designed with replaceability in mind, but the science was important enough that NASA engineers spent the better part of a year designing a repair kit that could be installed by a spacewalking astronaut, then training that astronaut to use it. The eventual repair, in January 2025, was an audacious feat of practical engineering. Patches were applied, Sunlight stopped leaking in. NICER returned to work. Why were astronomers so eager to get NICER back? Because before the damage, it had been starting to provide the most precise measurements of neutron star surfaces ever made. And from those surface measurements, astronomers were beginning to infer what was inside. The trick is that as a neutron star rotates, the hot spots on its surface, where the magnetic field channels charged particles down onto the crust, sweep into and out of view. The pattern of the resulting X-ray pulses depends, in subtle ways, on the radius of the star. If you can measure the pulse shape precisely enough, you can solve for the radius. Combine the radius with the mass, which can be measured independently by watching how the star tugs on a companion, and you have the average density. Combine many neutron stars with different masses, and you start to map the equation of state. NICER's most consequential measurement before the damage was of a particular pulsar called PSR J0740 plus 6620. Astronomers usually shorten it to J0740. We will spend a lot of time with J0740 in a few parts. For now, just hold the name. It is a pulsar that broke the standard story of what is inside a neutron star, and the rescue mission to repair NICER was largely about getting back to studying it. Before we get to the center, though, we need to walk down through the layers. So let us start from the outside and descend. The very outermost layer of a neutron star is its atmosphere. The atmosphere is about 10 centimeters thick. That is not a typo. The whole atmosphere is about as deep as the length of your hand. It is composed of hydrogen and helium, left over from the supernova that produced the star, or accreted from a stellar companion afterward. The density of the atmosphere is roughly that of diamond, about 3 or 4 grams per cubic centimeter, which sounds extraordinary until you realize that it is the lowest density layer in the entire object. Every layer below the atmosphere is denser. The atmosphere is also extremely hot. Right at the surface, the temperature can be 2 million degrees Celsius. The thermal radiation from this atmosphere is what NICER and other X-ray telescopes detect. The light you see when you look at a neutron star is, in a real sense, the light from a 10 centimeter deep layer of diamond density plasma glowing white-hot above the crust. Below the atmosphere, the density rises sharply. We enter the outer crust. The outer crust is composed of ordinary atomic nuclei iron at the top, then heavier and more neutron-rich nuclei as you descend embedded in a sea of degenerate electrons. The pressure is high enough that the electrons have been stripped off the atoms and form a free, degenerate gas, just like inside a white dwarf. The nuclei themselves are stationary, locked in a crystalline lattice. The crust is, in a sense, a giant single crystal of nuclear matter, with electrons flowing around the lattice like a fluid. The density at the top of the outer crust is around 10,000 kilograms per cubic meter. By the bottom, it is around 400 trillion kilograms per cubic meter, what physicists call the neutron drip density. The neutron drip is where things get strange. As you push deeper into the crust, the nuclei become more and more neutron-rich. There comes a point at a density of about 4 times 10 to the 11 grams per cubic centimeter where the nuclei simply cannot hold any more neutrons. Excess neutrons begin to leak out into the spaces between the nuclei, forming a free neutron gas alongside the existing electron gas. This is the inner crust. As you descend further, more and more of the matter is in the form of free neutrons rather than bound in nuclei. The ratio gradually tips. Near the bottom of the inner crust, almost all the matter is free neutrons, with only occasional clumps of more conventional nuclei. And then, near the very bottom of the crust, just before we enter the outer core, the laws of geometry start doing something nobody anticipated until they were simulated on a computer. The protons and neutrons that are still arranged in nuclei begin to deform. The pressure is so extreme, and the competition between the strong nuclear force pulling them together and the electromagnetic force pushing protons apart is so finely balanced that the nuclei cannot stay spherical. They stretch, they merge, they sheet up. They arrange themselves into geometric patterns that are not seen anywhere else in the universe. Physicists have named the resulting structures after pasta shapes. You sink into the neutron star, layer by layer, past the atmosphere, which is thinner than the width of a credit card and as dense as diamond, past the outer crust, where every atom has been crushed and the electrons have been peeled off into a shared sea, past the inner crust, where neutrons begin to drip out of nuclei and swim freely beside them. And then you reach the layer the physicists named after Italian food. The first layer of nuclear pasta is called gnocchi. The shapes are small spherical clumps of nuclear matter, similar to ordinary nuclei, but more densely packed, embedded in the surrounding electron and neutron sea. The clumps are roughly round, like little potato dumplings. As the pressure rises with depth, the gnocchi flatten and elongate into rods, which are called spaghetti, long parallel cylinders of nuclear matter, all packed beside each other like reeds. Press further, and the cylinders flatten into sheets, which are called lasagna flat planes of nuclear matter stacked one above the next, with the electron and neutron sea filling the spaces between them. Below the lasagna, the geometry inverts. Instead of solid sheets of nuclear matter in a sea of free particles, you get cylindrical voids cut into a continuous medium of nuclear matter. These are called anti-spaghetti. Below them, the voids become spherical, and the geometry is now nuclear matter pierced by spherical bubbles, anti-gnocchi, or what some physicists call the Swiss cheese phase. Below the Swiss cheese, the nuclei have effectively merged into a uniform medium, and we are entering the outer core. The whole nuclear pasta region, from the top of the gnocchi to the bottom of the Swiss cheese, is only about 100 meters thick, but it is the densest structured material in the universe. And, according to simulations, it is the strongest material the universe has ever produced. The estimated shear strength of nuclear pasta is around 10 billion times the shear strength of steel. The entire region weighs more than 3,000 Earths. Let me say that again, because it is hard to believe. 100-meter thick shell of pasta-shaped nuclear matter near the bottom of the crust of a neutron star weighs more than 3,000 entire Earth planets. The strongest material in the universe is named after the things you eat with red sauce, and it is found inside an object the size of a city, in the leftover core of a long-dead star somewhere out in the dark. The pasta layer is a place where ordinary nuclear physics has been deformed by gravity into something unrecognizable. The strong nuclear force, which binds protons and neutrons into nuclei, is normally the most powerful force in nature at short distances. Inside the pasta layer, the strong force is in delicate balance with the surrounding free neutron and electron pressure, and the resulting equilibrium is what produces the strange geometry. Crystalline lattices of spherical nuclei give way to bars, give way to sheets, give way to inverted sheets, give way to bubbles. The transition between any two of these phases is at least in simulation sharp. If you were small enough to walk through the pasta layer, the structure of the world around you would change every few centimeters of descent, from clumps to rods to planes to voids and out the other side into a uniform sea. We are not yet at the center. We have only just reached the boundary of the outer core. The strangest layers are still ahead. Part 8. The Star That Made No Sense. For decades, astronomers were reasonably confident they understood neutron stars. Not in every detail, nobody could simulate the inner core, and there were lively debates about what was at the very center, but the broad picture seemed settled. There were equations of state, dozens of them in fact, that different theory groups had calculated based on different assumptions about how dense nuclear matter behaves. the observations all clustered in roughly the same place. The standard picture was that the most massive neutron stars should be the smallest ones, because more mass meant more gravity, and more gravity meant more compression. As you piled mass onto a neutron star, its radius would shrink. There was scatter in the predictions, but the qualitative behavior was unanimous. Heavier means smaller. Then NASA started measuring radii precisely, and the picture came apart. The first hint of trouble came in 2010. A team led by Paul Demarest, using the Green Bank telescope in West Virginia, weighed a pulsar called PSRJ1614 minus 2230 by watching how its orbit was distorted by the gravitational field of its white dwarf companion. The Shapiro delay a relativistic effect in which signals from the pulsar are slightly delayed as they pass near the companion. Let them solve for the pulsar's mass with extraordinary precision. The answer was 1.97 solar masses. That was unexpectedly heavy. Most existing equations of state predicted maximum neutron star masses well below 2 solar masses. The Demarest result, which was published in Nature, was a clean falsification of a large family of those equations of state. The pattern repeated. In 2013, another pulsar, PSR J0348 plus 0432, came in at just over 2 solar masses. In 2019, NICER and a parallel radio measurement nailed down PSR J0740 plus 6620. The star, whose name you have now seen several times at 2.08 solar masses, give or take a tenth. In 2022, PSR J0952 minus 0607, the so-called Black Widow pulsar, was measured at 2.35 solar masses. Each new measurement was higher than the previous one. Each killed off more equations of state. The equation of state catalogue was being culled in real time by the actual universe. But the truly strange result, the one that broke the standard picture rather than just trimming it, was the radius of J0740. The standard picture said that a 2.08 solar mass neutron star should be small, compressed by its own enormous gravity, maybe 10 kilometers in radius, maybe smaller. What NICER measured in 2019 and refined in 2021 was a radius of about 12.5 kilometers. That is essentially identical to the radii of neutron stars with only 2/3 of J0740's mass. The most massive neutron star in the careful measurement catalogue was the same size as a typical neutron star. That should not happen. It is not a small discrepancy. It is the opposite of what the standard picture predicted. The most carefully measured neutron star in the catalogue was, in 2021, a confession from the universe that nobody knew quite what was inside it. Let me sit with this for a moment, because it is the central pivot of the entire video. For decades, the assumption had been that as you piled mass onto a neutron star, the inside of the star would soften in some way, probably by converting some of its neutrons into quarks at the core, which would release a small amount of energy and reduce the resistance to gravity. A softer core means a smaller star at a given mass. The data on J0740 says the opposite. The data says that whatever is at the core, when you push hard enough on it, it pushes back harder than expected. The equation of state for the densest matter in the universe is stiffer than physicists had assumed. The interior of a neutron star is more resistant to gravity, not less. This is what physicists mean when they say J0740 broke the model. It is not that the star is doing anything impossible. It is that the inside of it is doing something nobody had predicted. The equation of state has to be hard. The standard assumption that the core would be a quark soup, which would soften the equation, is now in trouble. The standard assumption that the core would contain hyperons particles with strange quarks, which we will get to in the next part, is in worse trouble because hyperons should soften the equation of state even more. Something inside J0740 is harder than either of those models can produce. This is the moment in the descent where we no longer have a confident answer. We know the star is there. We know its mass. We know its radius. We know that, by all rights, its interior should be doing something. But the standard ideas about what that something is have just been falsified. The candidates that remain are stranger, more exotic, and in some cases, not even directly testable. The most massive object in the catalogue is, today, a confession. J0740 is the right mass and the wrong size. We thought we understood what was at its center. We were wrong. Every assumption that physicists had layered onto the inside of these objects, every equation of state, every model of the inner core, every story about what neutron matter does when it is squeezed past nuclear saturation, has had to be rewritten because of a single, careful weighing of a single, distant pulsar. The thing you are most sure of, when you weigh it precisely enough, may turn out to have a center you have never met. That is one anomaly. There are others. In 2022, the team that had measured the Black Widow pulsar at 2.35 solar masses pointed out that this mass appears to exceed the maximum allowed by the simplest version of the Tolman-Oppenheimer-Volkoff calculation, the upper bound on neutron star mass that we will get to in part 12, and that, again, the interior must be doing something the standard models did not predict. In 2024, a team led by Alessio Marino at the Institute of Space Sciences in Barcelona used the Chandra and XMM Newton X-ray telescopes to measure the surface temperatures of 3 nearby neutron stars. Neutron stars cool over millions of years as they radiate away their leftover heat, either through ordinary blackbody emission from their surfaces or through neutrino emission from their interiors. The cooling rate depends sensitively on the interior structure and the equation of state. Different interiors cool at different rates. By measuring how cool the 3 stars were, given their ages, the Marino team could constrain which equations of state were compatible with the data. The result was a massacre. The 3 stars were between 10 and 100 times cooler than other neutron stars of similar age. The discrepancy was so large that it ruled out approximately 3/4 of all the equations of state that physicists were currently considering. Whatever the correct equation of state is, it survived a culling that eliminated 3/4 of its competitors. The Marino result, combined with the J0740 radius, has narrowed the field considerably. There are still options. They are no longer the obvious ones. So what is left? What are the candidates for the center of a neutron star that survive the cull? There are 4 serious ones. They are not mutually exclusive. The right answer may involve 2 or more of them in combination, but they are conceptually distinct. The first is quark matter, in some form, possibly as color superconducting quark pairs rather than the simple quark soup that has been ruled out. The second is hyperons, possibly stabilized by 3 body forces that nobody has yet pinned down. The third is dark matter, accumulated by the star's progenitor over billions of years and dragged down into the core during the supernova. The fourth is a Bose-Einstein condensate of paired neutrons, in which the densest matter in the universe is simultaneously the most coherent quantum state in the universe, a single matter wave the size of a city. We will walk through all 4 in the next part. The point to hold for now is that the center of a neutron star is, in 2026, the densest object physics knows about that has an unknown contents. We have weighed it. We have measured its temperature. We have measured its radius. We have ruled out most of the things we used to think it was. We have not yet established what it is. The candidates are extraordinary. The data is incomplete. The answer is somewhere out there, in a pulsar we have already named. Part 9. 4 candidates for the center. There are 4 serious answers to the question of what is at the very center of a neutron star, and we are going to walk through them one at a time, slowly, because each one is its own small worldview. None of them is confirmed. Each of them is consistent with at least some of the data and inconsistent with at least some of the rest. The point of this part of the video is not to land on a winner. The point is to give you the lay of the land of an unsolved problem, so that you can hold in your head the 4 versions of reality that are currently competing for the title of densest possible state of matter. The first candidate is quark matter. To explain it, we have to descend one level below the neutron itself, into the substructure of what we used to think of as the building blocks of atoms. Neutrons and protons, as it turns out, are not fundamental. They are themselves composite objects, each made of 3 smaller particles called quarks. There are 6 known kinds of quark, labelled, somewhat whimsically, up, down, strange, charm, top, and bottom. Ordinary matter is built out of just 2 kinds, up and down. A proton is 2 ups and a down. A neutron is 2 downs and an up. The other 4 flavors of quark exist, but they are heavier and shorter lived, and they show up only in high-energy particle physics experiments and in cosmic ray collisions, not in any matter you encounter day to day. The strong nuclear force, mediated by particles called gluons, binds the quarks together inside each proton and each neutron with extraordinary tightness. This binding is so strong that, under ordinary conditions, you cannot extract a single isolated quark. If you try to pull a quark out of a proton, the energy you put into the pull is converted into new quark-antiquark pairs, and the quark you are pulling on always ends up bound inside some new composite particle. Isolated quarks have never been observed. This phenomenon is called confinement, and it is one of the defining features of the strong force. But confinement may have a limit. At sufficiently high density, the binding between quarks may break down, and the quarks inside neighboring protons and neutrons may merge into a continuous sea of free quarks, a quark soup, sometimes called a quark-gluon plasma. This is the kind of matter that briefly exists in heavy ion collisions at the Large Hadron Collider and the relativistic Heavy Ion Collider, where gold or lead nuclei are slammed together at near light speeds to recreate, for a fraction of a second, the conditions of the very early universe. In those experiments, the quark-gluon plasma lasts for about 10 to the minus 23 seconds before it cools, and the quarks recombine into ordinary particles. The proposal is that inside the densest neutron stars, the pressure is high enough to maintain a quark soup permanently in the core. There is a refinement of the idea due to Edward Witten in 1984 and earlier work by Bodmer in 1971, which proposes that not all quark soups are unstable, that a soup containing roughly equal numbers of up, down, and strange quarks may actually be the true ground state of nuclear matter, more stable than ordinary protons and neutrons. Such matter is called strange matter, and a star made entirely of it is called a strange star, or a quark star. The problem, as discussed in the previous part, is that the simplest quark soup models predict a soft equation of state, and J0740 says the equation of state is hard. There are more sophisticated quark models, color superconductors, in which quark pairs become coherent over macroscopic distances, and various hybrid models in which the outer parts of the star are conventional neutron matter, and only the inner core is quark matter that can produce harder equations of state. But the simple version of quark matter as the core of a neutron star is now in serious trouble. The second candidate is hyperons. A hyperon is a baryon, a composite particle of 3 quarks that contains at least one strange quark, The lightest hyperons are the lambda particle and the sigma particles, which contain one strange quark each. They were discovered in cosmic ray experiments in the 1940s and 1950s. In the laboratory, a free hyperon decays in about 10 to the minus 10 seconds. In the dense interior of a neutron star, however, the energy cost of converting a high-energy neutron into a lambda becomes favorable at sufficiently high density, and a population of stable hyperons should build up. The trouble with this picture is exactly the same as the trouble with the quark soup. Adding hyperons softens the equation of state. The energy cost of producing a hyperon is small, but the hyperons are then locked in low-energy states by the Pauli exclusion principle, and they no longer contribute to the outward pressure as effectively as energetic neutrons. The expected result is a softer equation of state, which means smaller maximum neutron star mass, which means hyperons should not be present in J0740. This is the hyperon puzzle. The puzzle has been live for more than a decade, and the leading proposed resolutions involve three-body nuclear forces that prevent the hyperons from forming, or that stiffen the equation of state when they do, or various combinations of quark deconfinement and chiral effects that nobody has yet pinned down on the lattice. The hyperon puzzle is not solved. It is open. The third candidate is dark matter. This is where Fritz Zwicky's other big idea from the 1930s intersects with his proposal of neutron stars. Dark matter is, by mass, the dominant form of matter in the universe, roughly 5 times as much of it as ordinary matter, by Planck's satellite measurements of the cosmic microwave background. We do not know what it is. We know it has mass, because galaxies and galaxy clusters move as if there is more mass present than the visible stars can account for. We know it does not interact strongly with light, because we cannot see it. We know it does not interact strongly with ordinary matter through any force other than gravity, because if it did, we would have detected it in direct detection experiments by now. But dark matter is everywhere. The galaxy is full of it. As a massive star moves through the galaxy over its 100-million-year lifetime, it slowly accumulates dark matter through gravitational capture, and that accumulated dark matter sinks to the center of the star. When the star eventually goes supernova and leaves behind a neutron star core, the dark matter goes along for the ride. It is now sitting in the center of the neutron star, contributing to its mass, its pressure, and its equation of state. Studies over the last 15 years have shown that admixing dark matter into a neutron star can harden the equation of state. The dark matter does not interact with the surrounding nuclear matter through the strong force, but its own pressure adds to the total resistance against gravity. The amount of dark matter required to explain the J0740 anomaly is small, a few percent of the star's mass, perhaps. But the implication is enormous. If this picture is right, then the center of a neutron star is the only place in the universe where dark matter is concentrated densely enough to be felt by ordinary matter through anything other than gravity. The dark matter problem and the equation of state problem become the same problem, and the inside of a neutron star is the only laboratory anyone has access to that can hold a controlled experiment on them. The fourth candidate is a Bose-Einstein condensate. To explain this one, we need to go back to 1924 and to Satyendra Nath Bose. Bose was an Indian physicist, a contemporary of Meghnad Saha at the University of Calcutta, born in 1894. He was a self-described perfectionist who loved the poetry of Tennyson. He chose physics, and by the early 1920s, he was working on a new statistical description of the behavior of certain classes of particles. Struggling to get his ideas published in English-language journals, he took a chance and wrote directly to Albert Einstein. The letter began, "Respected Sir, I have ventured to send you the accompanying article for your perusal and opinion." Einstein read the paper, was impressed, translated it into German himself, and submitted it to a prestigious German journal for publication. Bose-Einstein statistics was born. Bose-Einstein statistics describes the behavior of particles called bosons particles with integer spin, including photons of light and certain composite particles. Bosons have a peculiar property. They like to occupy the same quantum state. The more of them you put into a single state, the easier it becomes for additional bosons to join. Below a critical temperature, a gas of bosons will spontaneously collapse into a single quantum state and behave collectively as one giant matter wave. The result is called a Bose-Einstein condensate, and it was first produced in a laboratory in 1995. Neutrons, however, are fermions. They have half-integer spin. They obey the Pauli exclusion principle. They cannot share quantum states, which is exactly why neutron degeneracy pressure works in the first place. So how can there be a Bose-Einstein condensate inside a neutron star? The answer is pairing. Two neutrons can, under the right conditions, pair up to form a composite particle whose total spin is an integer. The composite particle is a boson. It can join a Bose-Einstein condensate. The pairing is analogous to the Cooper pairing of electrons that produces superconductivity in cold metals. If neutrons in the core of a neutron star pair up in this way, the paired neutrons can condense into a coherent quantum state, and the resulting condensate provides an additional source of outward pressure beyond ordinary degeneracy. The equation of state hardens. Massive neutron stars can be larger than the simple models predict, which is exactly what J0740 looks like, the same quantum refusal we have been carrying with us since Fowler. The first time, the refusal was electrons in a white dwarf, modest, lab-scale physics applied to a star. The second time, it was neutrons in a neutron star, the same exclusion principle, now operating on the densest matter in the universe and barely holding. If the Bose-Einstein condensate picture is right, the third version of the same idea is now operating at the very center, with paired neutrons behaving as bosons and condensing into a single macroscopic quantum wave. The densest matter in the universe is also, in this picture, the most quantum coherent, a single matter wave the size of a city. We do not know which of these four candidates is right. We do not know that any of them is right. The data is consistent with several of them and with combinations. The point that the whole video is building toward is that the inside of a neutron star is the universe's last word on what dense matter can become, and we are still waiting for the universe to finish telling us the answer. Part 10. 5 versions of wrong. Every time a major scientific question is unresolved, there is a parallel conversation going on outside of mainstream science. Some of it is reasonable speculation by amateurs. Some of it is fringe science by people who have done a serious amount of reading but reached unconventional conclusions. Some of it is straight up wrong in a way that the data has been able to falsify cleanly. Neutron stars, because they are so extreme and because their interiors are unresolved, attract more than their share of all three kinds of conversation. Let us walk through the most common alternative angles and what the data actually says. The first one is the claim that neutron stars are not really neutron stars at all, that they are actually black holes wearing a kind of mask. The proponent of this idea, an Indian astrophysicist named Abbas Mitra, has argued since the late 1990s that classical general relativity does not actually permit a black hole event horizon to form in finite time, and that what we observe as black holes and neutron stars are instead long-lived collapsing objects he calls eternally collapsing objects. The idea has some mathematical content. It has not survived contact with the data. The Event Horizon Telescope's images of the black holes at the center of our galaxy and at the center of the galaxy M87 both show photon rings that match the predictions of Einstein's general relativity for a black hole with an event horizon at the few percent level. LIGO observations of black hole mergers show post-merger ring-down signals consistent with the horizon damping behavior of a Kerr black hole. The eternally collapsing object framework cannot reproduce these observations without unnatural fine-tuning. Most working astrophysicists treat it as a curiosity, not a serious alternative. The second one is the proposal that quark nuggets, sometimes called strangelets, make up the dark matter. The idea, due originally to Witten in 1984, is that small clumps of strange quark matter, with masses between about 100 grams and 100 kilograms, may have been produced in the early universe and could be drifting through the galaxy today. Such objects, on contact with ordinary matter, would convert it to strange matter. They would essentially be the zombies of cosmology. Anything they touched would become more of them. Various experiments have searched for them. The IceCube Neutrino Observatory, under the Antarctic ice, looks for the subatomic shrapnel they would produce when they hit the upper atmosphere. Seismic surveys have searched for the tracks they would leave through the Earth. Detailed analyses of dark matter constraints have shown that most of the relevant parameter space is now ruled out. Strangelets are not the dark matter. They may exist at much smaller masses, in which case they would not contribute meaningfully to dark matter and would be detectable only as occasional unusual events in particle physics experiments. There is, as of today, no clean detection. The third alternative is older and more romantic. It is the idea that pulsars are not natural, that the regular pulses we receive from them are signals from extraterrestrial civilizations. This was, briefly, taken seriously in the immediate aftermath of Jocelyn Bell Burnell's 1967 detection of the first pulsar. The signal she found was so regular, so artificial seeming, that the provisional name in her lab notebook was LGM1, standing for Little Green Men No. 1. The natural explanation that the signal came from a rotating neutron star whose magnetic field channeled beams of radio waves out from its poles like a lighthouse was on the table from very early. Within a year, additional pulsars had been discovered, all with similarly precise pulses but with different periods, distributed across the sky in ways that fit the natural explanation perfectly and made the alien beacon explanation impossible without a coordinated network. The aliens' hypothesis quietly died. It reappeared briefly with the discovery of fast radio bursts in the late 2000 and 7th millisecond duration radio pulses coming from extragalactic sources, and the leading explanation today is that fast radio bursts come from flares on magnetars, the most extreme magnetic neutron stars. Pulsars are not aliens, they are corpses. The fourth alternative is one that comes mostly from science fiction, but that I think is worth mentioning because the underlying physics is real. Robert L. Forward, in his 1980 novel Dragon's Egg, imagined a civilization of microscopic creatures called Chela living on the surface of a neutron star. The Chela, in the novel, evolve in compressed time because of the gravitational time dilation at the neutron star's surface. The biology is impossible. Surface gravity instantly crushes any structure larger than a fraction of a millimeter, so there is no room for Chela of any kind on any neutron star. But the time dilation reasoning is real. Clocks on the surface of a neutron star tick at about 70% of the rate of distant clocks. A second on the surface is about 1.4 seconds outside. If you could put a stopwatch on the surface of a neutron star and run it for a year, your friends in distant space would clock you at about a year and a half. The compression of time near these objects is genuine, even if the civilizations are not. The fifth and final alternative is the claim that neutron stars produce gravitational anomalies on Earth, that their influence can be felt locally, that they cause earthquakes or weather changes or strange biological effects. There is no credible mechanism for this. The nearest known neutron star is several hundred light-years away. Its gravitational influence on the Earth is many orders of magnitude smaller than the influence of distant cars driving on a freeway near your house. If a magnetar passed within a few light hours of Earth, which it will not, statistically its magnetic field would distort atomic structure significantly, and we would have problems. But that is not happening. The claim is worth debunking only because it circulates, and because anyone who has spent time around speculation about extreme astrophysical objects will eventually hear someone make it. Why are we walking through all these wrong answers? Because the right answer is genuinely unknown, and one of the things that makes a scientific mystery feel uncomfortable is the way the absence of an answer attracts speculation. It is worth being clear about what we do know and what we do not know and where the lines fall. We know that the inside of a neutron star is not a black hole wearing a mask. We know that quark nuggets are not the dark matter. We know that pulsars are not alien beacons. We know that microscopic civilizations cannot live on the surface, even if time is genuinely strange there. We know that distant neutron stars do not affect the Earth. What we do not know is what is at the very center. We do not know whether it is a quark soup, or hyperons, or dark matter, or a Bose-Einstein condensate, or some combination, or something nobody has yet imagined. We have weighed the center. We have measured its radius. We have ruled out most of the simple models. We have built telescopes and gravitational wave observatories specifically to keep narrowing the question, and we are still narrowing it. This is, in my opinion, the most scientifically honest place a deep dive about neutron stars can land. The interior of these objects is one of the few remaining places in physics where the experts genuinely do not know the answer to a clean question and where they are not certain that any of the currently considered answers is correct. There is room here for the next theoretical breakthrough. There is room here for the next observational surprise. There is one more piece of the story to tell before we close the limit on how heavy a neutron star can possibly be. The moment in 2017 when astronomers first watched two of these objects merge, and the question of what happens when the universe finally runs out of safety nets. The Tolman-Oppenheimer-Volkoff limit. The final tightrope. The moment when even neutron degeneracy fails, and the universe has nothing left to offer. That is the next and last part of the descent. Part 11. The limit of the last refusal. Mikhail Volkov swings an axe at a tree. The wood is frozen. He is sick, he is thin, and he is in the Soviet Arctic. He is a prisoner in one of the gulags Joseph Stalin built across the northern half of his country during the years of the Great Purge. Mikhail came back to the Soviet Union in 1936, leaving Canada because relatives in Russia had assured him that things were not as bad as the reports suggested. The relatives were wrong. Mikhail entered the Gulag almost immediately on his arrival. He will die there in a few years, never having seen Canada again. He left his family behind in North America when he went. His son, George, was 22 and still living in California. That same year, George Volkov began graduate work at the University of California, Berkeley, under a man who would later become very famous for somewhat different reasons. The man was J. Robert Oppenheimer. Within a few years, the pair would be working together on the Manhattan Project to develop the first atomic bomb. But before the war, before the bomb, before Los Alamos and Hiroshima, and all of the history that followed, George Volkov and Robert Oppenheimer collaborated on a calculation that quietly, in a paper published 7 months before the Second World War broke out in Europe, set the upper limit on how heavy a neutron star can be. The collaboration also included a third physicist, Richard Tolman, working from the California Institute of Technology. The three of them, building on a calculation that Tolman had started independently, derived the relativistic equation of hydrostatic equilibrium for a non-rotating spherical body and applied it to a sphere of neutron degenerate matter. The result is now called the Tolman-Oppenheimer-Volkoff equation, and the maximum mass it predicts for a neutron star is called the Tolman-Oppenheimer-Volkoff limit, or simply the TOV limit. The original calculation in 1939 gave a TOV limit of about 0.7 solar masses, which was less than the Chandrasekhar limit for white dwarfs. That made no sense, because the calculation predicted that no neutron star could be heavier than a white dwarf, which would mean that the path of collapse from white dwarf to neutron star, the path we have spent this whole video walking, could not occur. The original answer was wrong. The reason it was wrong is that Oppenheimer and Volkoff had used an equation of state that treated the neutrons as a non-interacting Fermi gas. They had not accounted for the strong nuclear force, which provides additional outward pressure at high density. By the 1990s, with more sophisticated equations of state that included realistic nuclear interactions, the TOV limit had been revised upward to somewhere between 2 and 3 solar masses, depending on which equation of state you used. The precise value of the TOV limit, however, was unknown until the universe finally gave us a way to measure it. The measurement came on August 17, 2017. In the summer of 2017, the astronomical rumor mill went into overdrive. It started when an astronomer named Craig Wheeler posted a cryptic tweet on the 18th of August. The tweet read, "New LIGO source with optical counterpart, blow your socks off." Internet sleuths immediately began checking the observation logs of every major telescope they could access, and found that dozens of telescopes had been hastily redirected to stare at the same galaxy 140 million light-years away, called NGC 4993. It took 2 more months for the official announcement to come. When it did, the announcement reshaped astrophysics. What had happened was this. The day before Wheeler's tweet, the Laser Interferometer Gravitational Wave Observatory had detected a signal lasting about 100 seconds. The signal was the characteristic chirp of 2 neutron stars spiraling in toward each other, the frequency and amplitude of the gravitational waves climbing as the 2 stars came closer and rotated faster. The final moment of merger was lost to the detector noise, but the preceding spiral-in was beautifully clear. 2 seconds after the gravitational wave signal ended, a flash of gamma-ray light arrived from the same patch of sky. Over the next hours and days, telescopes across every continent and in space pointed at the location and watched the optical, ultraviolet, infrared, X-ray, and radio afterglow of the collision. 70 different observatories contributed data. The event was given the name GW 170817. It was the first time astronomers had ever directly observed the merger of 2 neutron stars. It was also the first time gravitational waves and electromagnetic radiation had been detected from the same source. The combination is now called multi-messenger astronomy, and it has become one of the most important new methods in 21st century astrophysics. For our story tonight, GW 170817 did 3 things. First, the 2-second gap between the gravitational wave signal and the gamma-ray burst was used to constrain the speed of gravity, which turned out to be the speed of light to within 1 part in 1,000 trillion. Several alternative theories of gravity that predicted a slightly different speed for gravitational waves were falsified in a single observation. Second, the optical afterglow contained spectroscopic signatures of newly synthesized heavy elements, gold, platinum, uranium, confirming that neutron star mergers are a major source of heavy element nucleosynthesis in the universe. The gold in your jewelry probably came from one of these collisions billions of years ago. And third, the tidal deformability of the 2 pre-merger neutron stars, as inferred from the shape of the gravitational wave signal during the final stages of the spiral-in, narrowed the TOV limit to between about 2.01 and 2.17 solar masses. That is the strongest constraint we have on the maximum mass of a neutron star. Anything heavier than about 2.2 solar masses in a non-rotating star cannot exist. The neutrons cannot hold it up. Even neutron degeneracy pressure, the final form of quantum refusal, fails at that limit. When the gravitational waves from GW 170817 reached Earth in August of 2017, they had been traveling for 140 million years, ringing through spacetime the entire time. 2 seconds after the last wave passed through the detectors, a flash of gamma-ray light arrived from the same patch of sky. The 2 seconds across 140 million years told us the speed of gravity is the speed of light, to 1 part in 1,000 trillion. The collision that produced both signals was 2 neutron stars finding each other after a long, slow spiral inward. Whatever they were made of when they met, quark soup, condensate, dark matter, something nobody has named, yet they are no longer that now. They are either a quark star, briefly, or a black hole, forever. The universe gave us a single chance to read what was inside them, and we used it. The combined mass of the 2 pre-merger neutron stars in GW 170817 was about 2.8 solar masses. That is well above the TOV limit. So when the merger happened, the combined remnant could not have remained as a stable neutron star. It either collapsed almost immediately into a black hole, or it briefly survived as a hypermassive neutron star supported by rapid rotation before collapsing, or it transitioned through a brief, intermediate quark star phase before becoming a black hole. The observational data is consistent with several of these scenarios. We do not know exactly which one happened. We do know that, by minutes after the merger, the remnant was a black hole. This is the moment in the story when the universe runs out of safety nets. Below the TOV limit, neutron degeneracy holds the star up. Above the TOV limit, it does not. There may, briefly, be one more step of resistance, the quark star phase, in which the quark soup itself provides slightly more outward pressure than the broken neutron degeneracy. But above some slightly higher limit, even that fails, and the collapse continues all the way down to a black hole. The final tightrope is uninspected. We have only ever observed the moment after it broke. The same characters we have followed all night are now in their final scene. Gravity, the Mr. Hyde of stellar physics. Heat, the first safety net, present in the Sun and in main sequence stars. Electron degeneracy, the second safety net, present in white dwarfs and the outer layers of neutron stars. Neutron degeneracy, the third safety net, present in the cores of neutron stars below the TOV limit. And then nothing, or possibly one more step, the quark phase, that we have only inferred and never directly weighed. Above the TOV limit, Jekyll loses, and the universe gives back nothing more. The descent that started at the surface of the Sun, with the Parker Solar Probe skimming the corona on a Christmas Eve, ends here. At the moment when the final form of resistance fails, and the matter falls forever into a place where the laws of physics, as we understand them, no longer describe what is happening. This is the universe's last word on matter. Above the TOV limit, there is no matter. There is only the warped geometry of spacetime around a singularity. The story of dense matter ends. Whatever was inside those 2 neutron stars before they merged is gone, and we will never directly hold it. We have been walked all the way to the bottom of one of the strangest objects in the universe, and we have been left there, by design, without an answer. Part 12. The unfinished answer. At the very centre of a neutron star, in the densest place ordinary matter has ever found itself, there is a question without an answer. We have weighed the question. We have measured its size and its temperature. We have built telescopes specifically to see what is at the bottom of it. We have rebuilt those telescopes in space, with spacewalking astronauts when they broke. We have listened to space-time ring after collisions 140 million light-years away. And we still do not know. The descent we have made tonight is the descent of stellar physics into the densest regime any of its tools can reach. The Sun, with its core of ionized hydrogen at 15.7 million degrees and 150 grams per cubic centimeter, is the easy case. The white dwarf, with its electron-degenerate carbon-oxygen crust and its sugar cube weighing as much as an elephant, is the first encounter with quantum matter holding up a star. The neutron star, with its diamond density atmosphere, its crystalline crust, its nuclear pasta layer 10 billion times stronger than steel, its outer core of superfluid neutrons, and its inner core of unknown contents, is the second. And the center of that inner core is the third, and we have not yet been allowed to see what is there. There is one more thing I want to say about why this matters, because it can sound across 2 hours of pasta-shaped nuclear matter and Bose-Einstein condensates and cold neutron stars in Barcelona like the question is a curiosity. It is not a curiosity. The matter inside your body, the floor under your feet, the chair you are sitting in or the bed you are lying on right now, all of it follows the same physics that breaks down inside a neutron star. The protons and neutrons in your own bones are made of the same quarks that may or may not be deconfined in J0740's inner core. The dark matter that may be admixed in that core is the same dark matter that holds the Milky Way together. The Bose-Einstein condensate that may be holding up the densest matter in the universe is governed by the same statistics that Satyendra Nath Bose worked out in 1924, the same statistics that govern superfluid helium and laboratory atomic condensates, and the photons in this video's voiceover. To ask what hides at the center of a neutron star is to ask the same question as what is matter, really. And the universe has not yet given us the answer. There are more measurements coming. NICER is back in operation after the 2025 repair, and it is continuing to map pulsar surfaces and refine the radius measurements that constrain the equation of state. LIGO, Virgo, and CAGRA are continuing to operate, and they catch more neutron star mergers every observing run. Each new merger waveform tightens the constraint on the tidal deformability and, through that, on the equation of state of the dense interior. The next generation of gravitational wave observatories, the Einstein Telescope in Europe and the Cosmic Explorer in the United States, are planned to come online in the 2030s. They will catch every neutron star merger in the visible universe, which means hundreds of them per year. The equation of state will be constrained, not loosely as it is today, but precisely. There are also laboratory developments to watch. Heavy ion collisions at the Large Hadron Collider, the Relativistic Heavy Ion Collider, and the planned FAIR facility in Germany continue to push the recreation of quark-gluon plasma to higher densities. At some point, the laboratory experiments and the astrophysical observations will converge on the same regime, and we will be able to compare directly. Lattice quantum chromodynamics, the computational technique that simulates the strong force from first principles, still has a sign problem at high baryon density that prevents direct simulation of the neutron star interior. If that bottleneck breaks through some new computational algorithm, through a fundamental theoretical insight, through quantum computing, perhaps the inside of a neutron star will become directly calculable for the first time. We are not there yet. Most likely, the answer to what is at the center of a neutron star will not come from one decisive measurement. It will come from the convergence of many. A precise radius measurement here, a merger waveform there, a new equation of state from improved nuclear physics, a consistent picture slowly assembled from independent lines of evidence that points to one answer and rules out the others. The process is the normal way physics resolves hard questions. It has been going on this particular question for the better part of a century. It is not yet finished. There is also the possibility, and this is the possibility that, in my view, makes the whole descent worth doing, that the answer, when we find it, will not be one of the four candidates we have walked through tonight. The original Tolman-Oppenheimer-Volkoff calculation in 1939 placed the maximum neutron star mass at 0.7 solar masses. We have since observed neutron stars more than 3 times that heavy. Every new measurement of these objects has been a small surprise, and every surprise has reshaped the picture of what the interior must contain. There is no good reason to think the surprises are finished. Whatever is at the center of J0740 may turn out to be something nobody has yet thought of, and the first hint of it may come from a measurement nobody has yet taken with an instrument nobody has yet built. At the center of a neutron star is the only place in the universe where you could put a sample of ordinary matter, push it as hard as the universe knows how to push, and watch what it becomes. The answer to that experiment is currently unknown. Every atom in your body has, in some sense, been waiting for it. Out there in the night sky, the Crab pulsar is still pulsing at 30 Hz. The signal has been arriving steadily since long before there were instruments to record it. It will continue to pulse for thousands of years, possibly tens of thousands, slowly losing energy and slowing down. Somewhere behind that signal, deep inside that 21-kilometer sphere, is the answer to a question physics has not yet finished asking. The signal is a steady drum. The drumbeat has been going since the year 1054. It will keep going. We are listening. And somewhere in the same galaxy, statistically right now, 2 more neutron stars are completing the long, slow spiral that ends in a merger. The gravitational waves from that collision are on their way. They will arrive in a few thousand years, or a few million. Some future astronomer, at some future detector, will measure the waveform and add another data point to the constraint on the equation of state. The puzzle will narrow further. The answer will come closer. The descent that you and I have just made together, from the sun's photosphere to the unknown center of a dead star, will be repeated, with a sharper conclusion at the bottom, by people who do not yet exist. Tonight, that is all I have. The tightrope is held by something we cannot yet name. The universe is built, layer by layer, out of refusals, electrons refusing to share states, neutrons refusing to share states, and at the deepest layer, possibly something refusing in a way nobody has yet described. The refusal works. The star is up there. The data is real. The answer is coming. Until it comes, the center of a neutron star is the place where physics gets to keep an open verdict, where the rope is still being held by hands we have not seen, and the tightrope walker is still walking in a place we have not yet been allowed to reach. Good night,